Hi, and welcome to another video. This one will be about Fibonacci numbers modulo a prime. Well, it has to be an odd prime. Okay, so let me get my pen started. All right, so these numbers that we're studying are called the Fibonacci numbers, and you have probably heard of them before. It's the sequence that you start with f0. So these are the numbers fn. You start with f0 equals 0, f1 equals 1, and then fn plus 1 is equal to fn plus fn minus 1. All right, so let's just make a little table of some Fibonacci numbers. So here's n and here's fn. So we already said 0 is 0. Here, let me write all the numbers out first. 4, 5, 6, 7, 8, 9, 10. I want to go up to 12 for the examples. Okay, so 0 and then 1. You need to set the first two. And then from here you can get the rest of them. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34. I'm going to write a little smaller. 21 plus 34 is 55, 34 plus 55 is 89, and then 55 plus 89 is 144. Okay. So, what are we looking at? We are going to look in this video at FP, okay, where P is an odd prime. So that's, let's circle the odd primes. So 2 is a prime, but it's not odd. 3 is an odd prime, 5 is an odd prime, 7 is an odd prime, 9 is odd, but it's not a prime, 11 is an odd prime. Okay. Well, it's literally all the primes except 2. Okay, and so FP is, well, it's 2, then it's 5, then it's 13, then 89. But here's the pattern that we're going to look at. So we're going to look at FP. So F3 is equal to 2, okay? And what is that? Modulo 3, it's equal to minus 1 modulo 3, right? If 3 is 0, then 2 is minus 1. So that's mod 3. F5 is equal to 5, and that's obviously 0 modulo 5. So the remainder divided by 5 is 0. So now look at F7. F7 is equal to 13, which is, again, we have minus 1 modulo 7. And then, so 9 is not prime. F11 is equal to 89, which is congruent to, well, 88 is 0 because it's a multiple of 11. So 89 has to be 1. And I don't know why I wrote minus 3 here. I said minus 1 and I wrote minus 3. Okay. Hope that didn't annoy you too much. Mod 11. Okay. That's one thing that we're going to notice. So it seems like, well, we haven't noticed anything yet. We're just listing stuff out. And it always seems to be minus 1, 0, or 1 so far. But we've only done 4 examples, so we can't possibly know that. Let's also look at a different pattern. We note that this is negative 1. So why don't we, if we look at f of 3 plus 1, so f4, okay, we get 3. Okay, let's do this again. So f5, we had 0 here, so we add, we subtract 0 from 5, and so f5 is obviously 5. Okay. Now, how about f7? Okay, so f7 was negative 1 modulo 7. So we take 7 minus minus 1, so we add 1 again. And we look at f8, and f8 is 21. Okay, so now we're starting to see something. So 3 is a multiple of 3, obviously. 5 is a multiple of 5. 21 is not equal to 7, right? So far we've had just, like, it's not exactly equal, but 21 is a multiple of 7, right? And we see that this pattern continues because f so we don't add 1 this time, we subtract 1 because we had a different sign here. So 11 minus 1 is 10, and that equals 55, which is a multiple of 11. Okay? So that's the pattern that we're going to see here. So there's some kind of number. We get a number that seems to be minus 1, 0, or 1 whenever we take fp mod p. And then if you take fp, but in the index, you subtract whatever number you get here, you seem to get a multiple of p. Okay? That's the pattern. Okay? And we're going to state this more formally once we have some notation. Okay, but now we're gonna focus our attention back on this right here. Okay, we're gonna look at squares modulo p. So in F3, now this is kind of a little bit annoying here that we're gonna use F for Fibonacci numbers, but the field with 3 elements is also denoted F3, but we're gonna make it bold to denote the field. So in the field F3, 0 squared is equal to 0, obviously. 1 squared is equal to 1. And 2 squared is equal to 4, but 4 is 1 modulo 3. So 2 squared is also equal to 1. And that means that 2 is not square in F3. Okay? And this is going to come in later. 2 is the same thing as 5. So we're trying to say 5 is not square in F3. Okay, now let's look at F5. Well, in F5, let's ignore F5 because F5 doesn't, it's kind of a special case. All right, it's, yeah, this is 0. It's actually going to be the only 0 that shows up. So let's just ignore F5. Let's go straight to F7. So in F7, 0 squared is equal to 0, 1 squared is equal to 1, 2 squared is equal to 4, 3 squared is equal to 9, minus 7 is 2, 4 squared is equal to 16, and you minus the multiple of 7, so 14, you get 2. 5 squared is 25, minus 21 is 4, and 6 squared is equal to 36, minus 35, we also get 1. So we see that the squares mod 7 are 0, 1, 2, and 4. So 3, 5, and 6 are not squares. So again, we see 5 is not square in F7. So we saw 5 is not a square in F3, and 5 is not a square in F7, and we got minus 1 for 3 and 7. So if there's a relation here, then we should be getting 5, the opposite sign, so 5 should be a square in F11. And that's easy to see, because in F11, let's just go from the beginning and see when we hit a square, so, or see when we hit 5. So 0 squared is equal to 0, 1 squared is equal to 1, 2 squared is equal to 4, 3 squared is equal to 9, which is in F11 this time, 4 squared is equal to 16, and 16 is equal to 5 in F11, because, well, you subtract 11. So 4 squared equals 5. So 5 is a square in F11. Okay, so now we've seen now we've we've kind of noticed a pattern here, and this doesn't prove anything, but in fact we are going to prove that for an odd prime, the fp modulo that prime is going to be related to whether 5 is a square in fp. Okay, so to do that, we're going to define something called the Legendre symbol. So this is the Legendre symbol. For p and odd prime and x in fp, we write x over p. It's the Legendre symbol, and it's one of 3 things. It's 0 if x equals 0. It is 1 if x is not equal to 0 and is a square mod p, and it's minus 1 otherwise. Okay, so here we found that 5 is not a square mod 3, so we're trying to say here that 5, Legendre symbol of 5 over 3 is equal to minus 1, and that's exactly what we get here, minus 1. Okay, so here's what we're going to prove. So want to show that FP is congruent to x over p. Okay. Sorry, not x over p, it's 5 over p. 5 over p modulo p. And remember the second thing that we wanted, now we haven't, I tried to explain it in words, but now we have a good symbol for it. I was trying to say that you shift by, like you subtract the number you get here in the index, and then you get 0 mod p, you get a multiple of p. And so we can finally write that. So f of p minus 5 over p is congruent to 0 mod p. So we're going to be able to show both of these things. Okay? All right. And that's going to be the rest of the video. So this is a very long introduction, but hopefully you found it, interesting to actually work out some examples. I could have just started with saying, hey, here's what the Legendre symbol is, and we're going to prove this, but, hopefully you get a sense of the pattern that arises and, the actual examples. Okay, so first we're going to have a formula for the Legendre symbol. So formula for x over p. Okay, so we're going to show that x over p is equal to x to the p minus 1 over 2. Okay, and obviously this is in FP. So x is taken to be an element of FP, but you can also, say p is like 7, we can put like 530 in for x. That's not going to be an element of F7, but you can take sort of its image in F7 once you, like its remainder mod 7, and that's x. So we're going to allow ourselves to write integers here, and you'll know what it means just by taking its image. Okay, so yeah, we want to prove this. Well, what we do is strongly going to be, it's going to strongly rely on Fermat's little theorem, which says that x to the p minus 1 is equal to 1. Okay, in FP, so I guess mod p. And that's just because, well, in the multiplicative group has identity 1 and cardinality p minus 1. So of course, you take any element to the cardinality of the group, to the power of the cardinality of the group, you're going to get the identity. So that's sort of a group theoretic proof of this statement, but whatever. We're not really going to get too much into group theory or whatever. This is a pretty basic formula that I'm sure you've seen before. So that's Fermat's little theorem. So it's going to rely on this. Let's look at this formula here. So if so we know that x to the p minus 1 is equal to 0. Okay, that's what I just showed up here for any x, right? So this factorizes into x to the p minus 1 over 2 minus 1, and then x to the p minus 1 over 2 plus 1. Okay, so first let's just take x to not be a, let's take x not to be a power of p, or a multiple of p, i.e. like x is not 0. Because if x is 0, then obviously this is 0, and that's the first case. So we're in the second case where it's 1 or minus 1. But this shows that it's 1 or minus 1, right? So this formula here, this thing right here has to be 1 or minus 1, because this entire product is 0, and it's only 0 if one of these two are 0, right? Okay, so let's just say if x is square mod p, then x equals y squared. That's what being a square mod p is. And now we can put in, it'll be this one. So y squared, so yeah, x to the p minus 1 over 2 is equal to y squared to the p minus 1 over 2. But now the 2 and the other 2 cancel out, so you get that's equal to y to the p minus 1, which we know is 1. Okay? So if x is square mod p, then this thing is equal to 1, which means this first factor is 0. All right? And we know that there are, okay, so how many squares mod p are there? So this is a polynomial of degree p minus 1 over 2. So we can have at most p minus 1 over 2 solutions. And we want to show that those solutions are exactly the squares mod p. Well, we want to know how many squares there are mod p. Well, we look at x squared, it's the same thing as, I guess let's start with this. So p minus x squared is equal to p squared minus 2xp minus x, or plus x squared, sorry. But if we mod out by p, these are both 0, so that's equal to x squared. So p minus x squared is equal to x squared in the finite field fp. So that means that if you want to know all the distinct squares mod p, we just want to take 1 squared, 2 squared, 3 squared, all the way up to p minus 1 over 2 squared, like kind of the first half of fp, and you'll get different numbers, because if you're counting down the other way, you get p minus 1 squared, which is equal to 1 squared, and then p minus 2 squared, and that's equal to 2 squared. So like the second half of this list, like this list, I'm listing the two halves, one on top of each other. The second half of the list is equal to the top half of the list because of this equation here. So what I'm trying to say is there are p minus 1 over 2 distinct squares, modulo p, which means, and all of them are solutions to this first equation here. Okay, so now if x is not a square mod p, then it's not if it's not a square mod p, it doesn't satisfy this part, but it still satisfies this, so it has to satisfy this part. So I'm not going to write all that out, but we've proven this formula here. We've proven this formula here, saying that if x is a square mod p, then this is going to be equal to 1. And if x is not a square mod p, then this can't be equal to 1 because this has at most that many solutions. So it has to be equal to minus 1. And thus we've proved this explicit formula for the Legendre symbol. Okay. So that's that. That's the formula for the Legendre symbol. Let's just finish this box. So this is this is the formula for the Legendre symbol. Now we're going to prove the formula for the Fibonacci numbers. So kind of like changing track, but we're doing two things, right? We're trying to show that the Fibonacci numbers equal some Legendre symbols, so we need to know a bit about both. And now we're going to move towards the Fibonacci side. So here's a formula for Fn. Okay, so we have Fn equals 1 over the square root of 5, 1 plus the square root of 5, the n, minus 1 minus the square root of 5, the n, over 2. Okay, now this seems kind of, honestly, incredible if you just look at the formula, it kind of looks crazy. Like Fn, we've already shown, is always going to be an integer because you get it by adding more. You start with 0 and 1 and you're always adding them together, so you're always going to get an integer. On the right hand side here, though, it's not at all clear when you stare at this that this is an integer, right? You have square root of 5, which is some irrational number, and then you're taking it to some power n, you're dividing it by 2 to the n, okay, and then you divide by another irrational number. Like it's not clear that this is an integer. Okay, so I'm going to give a proof, I'm going to call it a proof sketch because I'm going to sort of go really fast. It's by generating functions. it's sort of the quintessential first example in a course for generating functions. So if you've never seen this before, the reason I'm going to go fast is because if you've seen anything about generating functions, you have probably seen this example. And if you've never heard of generating functions before, I hope this inspires you to go read more about generating functions. There's an excellent book by Wilf, is the author's name, and it's called Generating Function. I'm gonna write it. I'm gonna print it. Generating Functionology, all lowercase, all one word, and it's a really good book on generating functions if you've never seen that. Okay, but what do? The idea of generating functions is we take some sequence of numbers and we make them the coefficients of a power series. So this is a function, a power series in Z. You can use X if you want, and it's going to be f0 plus f1z plus f2z squared plus f3z cubed plus and so on. So it's a power series. It's an infinite polynomial, and the coefficients are exactly the Fibonacci numbers. Okay, so let's write it a little bit. So f0 is 0, so there's nothing there. 0 plus f1 is 1, so z. f2 is also 1, so it's z squared. f3 is 2, so it's 2z cubed plus and so on. The coefficients are going to be the Fibonacci numbers. Okay, well, so what happens when you take a power series like this and you multiply it by z? Well, so what does zg of z look like? Well, it's going to be z times f0 plus z squared times f1 plus z cubed times f2, right? I realize I didn't change the order around, but it doesn't really matter. Okay, so if this was the sum of n equals 0 to infinity f and z to the n, then this thing has been shifted, right? So this is the sum of n equals 1 to infinity f n minus 1 z to the n. So everything's been shifted. So this fn became fn minus 1, and we have to start at n equals 1 because obviously there's no f minus 1. And likewise, fzgz is going to be sum of n equals 2 to infinity fn minus 2 z to the. Okay, so what is gz minus z of gz minus z squared of gz? Well, if we write that all out, let's group the terms together. So we have f0 coming from the gz here, and then there's no constant term. There's no constant term here, and there's no constant term here. Okay, so that's all the constant terms. For the linear terms, the z part, we have f1 in the first part, f1, and in the second part we have in this minus zgz, we get f0. Oh, sorry, minus f0. Okay, and that's all timesing by z. And in the third one, we have f2 minus f1 minus f0 z squared. And you can see that for the rest, it'll be like this. So we have 3 minus f2 minus f1 z cubed. So it's plus. So we're adding all these together, and then it's going to go ... Okay, so f0 is 0, so there's nothing here. Okay, and likewise, so then here f1 is 1 and f0 is 0, so this is 1. So this is 1 minus 0. But f2 is equal to f0 plus f1 by the formula for the Fibonacci numbers that we even started with. So this is going to be 0, and this is going to be 0, and all the rest are going to be 0. And so on. So on the right hand side here, this whole thing is equal to z. Okay? Now, so what we've shown is that g of z, so dividing out by g of z and, dividing out by g of z and then moving to the other side, you get g of z is equal to z over 1 minus z squared. Okay? Now, the denominator here, has roots by the quadratic formula, it has roots 1 plus square root of 5 over 2 and 1 minus square root of 5 over 2. And this is a pretty famous number. It's called the golden ratio phi. And we'll call this, it's the complementary root, and we'll call it phi hat. Okay? So I'm not going to do this part because it's kind of computationally tedious, but you can, when your denominator splits into, factors into two linear, this is what I'm trying to say. So this is 1 minus 1 minus phi of z, 1 minus phi hat of z. So it factors into two, that's not what I'm trying to say. Not exactly what I'm trying to say. I'm trying to say this is z minus phi and z minus phi. Anyway, it factors into two linear polynomials here, and there's a partial fraction decomposition that you can get, and so g of z turns out to be equal to 1 over square root of 5. You just equate coefficients, and you get 1 over 1 minus phi of z minus 1 over 1 minus phi hat of z. Okay? And remember, we started with a power series whose coefficients were the Fibonacci numbers. So we got to figure out what the coefficients of this are. That's not so bad because you know from a calculus class that this 1 over 1 minus z is an infinite power series that looks like this. So it's 1 plus phi z plus phi squared z squared plus phi cubed z cubed, and so on. And then on the other side here you have 1 plus phi hat z plus phi hat squared z squared plus, and so on. Okay, meaning that the coefficient of z to the n here is the nth Fibonacci number. That's what we define gz to be. The coefficient of z squared, it's got to be f2. So the coefficient of z squared here is phi squared minus phi hat squared, sorry, right there, all over square root of 5. So that's what we have. So we see that fn, this implies that fn is equal to 1 over square root of 5, phi to the n minus phi hat to the n. And, well, the formula for that is right here, 1 plus square root of 5 over 2, 1 minus square root of 5 over 2, which gives us the formula right like that. Okay, so it's kind of a complicated formula, but once we know what phi and phi hat are, then it kind of reduces to something a little simpler, which is this right here. Okay, so now we are ready to prove. So now we're ready to prove that fp is congruent to 5 mod p. Okay, so first we're going to prove a little lemma. So first a lemma. That's right, this is 5 over p. So first we're going to have a lemma, which is going to be useful for both things that we're going to prove. So it's good to prove this lemma in general. So lemma is 2 to the n times f of n times a Fibonacci number. The n Fibonacci number is equal to 2 times the sum over all k odd, n choose k, 5 to the k minus 1 over 2. Okay, now this looks like an infinite sum, and I guess it is an infinite sum over all odd k, but n choose k only, it's 0 if k is smaller than 0 or if it's greater than n. So it ends up being a finite sum. Okay, so what's the proof of this? So the proof is, well, we have a formula for fn, so 2 to the n fn is equal to 1 over square root of 5, 1 plus square root of 5 to the n minus 1 minus square root of 5 to the n. Now, if you recall in the original formula, there was a 2 to the n in the denominator. We just moved it over here. Okay. But we know what a, this kind of looks like the binomial theorem, and we have two binomials here, so it makes sense we should probably expand those out. So what does the first binomial theorem say? Well, sorry, the binomial theorem says that this is the sum of all k equals 0 to n. So on this first binomial, we get 1 to the n minus k, square root of 5 to the k. Now here we minus the same thing, k equals 0 to n, 1 to the n minus k, but it's a minus 5 to the k. Okay, so minus 5 to the k is equal to, it's going to be 5 to the k if k is even. Sorry, square root of 5 to the k. And it's going to be minus square root of 5 to the k if k is odd, right? So if k is even, then the term on this side is equal to the term on that side, meaning because we're subtracting them, they cancel out. So the only terms that survive are 1 over square root of 5. Okay, the terms that survive are the ones that are odd. Sorry, I forgot the n choose k. So there's n choose k here, and there's n choose k. So n choose k. The terms that are odd, what's on this side is going to be negated over here, but then we subtract, and if you subtract two negated things, right, you subtract the negation of something from it, you're going to get twice the thing. So there's 2 here, and then we have n choose k, 1 to the n minus k, there's no point writing it, square root of 5 to the power of k. Okay, because it's square root of 5 to the power of k minus square root of 5 to the power of k. Okay, but now we're done. So this is equal to, so square root of 5 to the power of k, that's 5 to the k over 2. Let's just do that right now. K over 2, and then you minus 1 more here. So minus another half. So it's 2 square root k, or sum over all k odd, and choose k, 5 to the k minus 1 over 2. It's k over 2 minus half. All right, so that's the proof of this little lemma. The lemma is that, and that's gonna be super useful. So now we show that proposition fp is congruent to 5p mod p. Okay, so proof. So by lemma, 2 to the p fp is equal to the sum over all, twice the sum over all k odd, p choose k, 5 to the k minus 1 over 2. But now let's look at this p choose k here. So p choose k is equal to, well, it's if k equals 0, it's 1. Okay, if k equals p, it's also 1. But in all other cases, it's actually going to be equal to 0 because you get p. So if k not equals 0, k not equal to p, we get this. So it's p minus 1, all the way down to p minus k plus 1. Okay, and then on the bottom, we get k minus 1, all the way down to k, all the way down to 1. So there's a p in the numerator, and there's not going to be a p in the denominator to cancel it out because, well, k is smaller than p, and p is, yeah, it's not divisible by anything smaller than it, right? So this is going to be equal to 0 in fp. Okay, so the only ones we need to worry about in this sum, it looks like a big sum of p plus 1 terms, but the only terms that are non-zero are the ones where k equals 0 and k equals p. And furthermore, I mean, it's not even a sum over p plus 1 terms, it's a sum over just half of that because k equals 0, k is even, right? 0 is even. So the only term here is the p choose p case, like the k equals p case. So 2 to the p fp is equal to 2 times, yeah, this whole term collapses to just one term. So it's p choose p, 5 to the p minus 1, 2. All right. Well, 2 to the p, so since 2 to the p minus 1 is equal to 1, 2 to the p is equal to 2. This is Fermat's little theorem again. So 2 fp is equal to 2, 5 to the p minus 1 over 2. And so fp is equal to 5 to the p minus 1 over 2, which is, of course, equal to 5. The Legendre symbol, 5p. Okay, so we proved that. Now, I just want to have a little note. So we're going to prove the other thing next, the one that that shows that something's a multiple of p. So next, right? We want to show that f of p minus 5p is congruent to 0 mod p. We want to show that. So this is a number that's plus or minus 1, unless p is 5. And we already know that, what am I trying to say? You can prove this. So fn plus 1, fn minus 1, minus fn squared is equal to minus 1 to the n. Okay, so this can be proved by induction. It's pretty easy. You just, you prove the base case, and then you show that you expand fn plus 1 out, and maybe expand something else out too. But whatever, it's like just from so exercise, prove by induction from fn plus 1 equals fn plus fn minus 1. Okay. But if you take this, okay, then what does this mean for fp? That means that fp plus 1, fp minus 1, minus fp squared is equal to minus 1 to the p, but since p is odd, it's just minus 1. And fp we already know is congruent to that Legendre symbol mod p, so the Legendre symbol is going to be 1 or minus 1, and so 1 or minus 1 squared is going to be 1. So this, we're going to have minus 1 here. So this has to be 0. So we already know just from this formula that 1 of fp plus 1 and fp minus 1 has to be 0. But this says more, obviously. This says that, one of those has to be 0, but the thing that has to be 0 is actually p minus the Legendre symbol. And note, they can't both be 0, right? Because fp is equal to fp plus 1 minus fp minus 1. And we already know that fp is plus or minus 1. Okay, so they can't both be 0, because if this is 0 minus 0, you don't get plus or minus 1. Okay? So we already know exactly one of fp plus 1 and fp minus 1 has to be 0. And we're going to show now that it's fp minus the Legendre symbol. And for the rest, this actually holds even when p equals 5, like we showed up here, right? Well, okay. Well, right, it shows when, it holds when p equals 5, because 5 over p is going to be 0, and then fp was equal to 5, and 5 is 0 mod 5. So it worked when p equals 5, and now we'll just assume that p is not 2 and p is not 5 for the rest of the proof. So it's an odd prime that's not equal to 5. So let's prove. Let's prove this statement. No, sorry, not this statement. This statement, okay. All right, so how do we do that? Well, we'll apply the formula, the lemma, to p plus 1. So 2 to the p plus 1, p plus 1 is equal to, it's going to be 2 times the sum over all k odd, p plus 1 choose k, 5 to the k minus 1 over 2. Okay, now p plus 1 choose k is equal to p choose k plus p choose k minus 1. So that's that Pascal's triangle identity that sort of defines, you can get all binomial coefficients from. But we already know, so if k equals, if k equals, k equals 0, this is p plus 1, get p plus 1. If k equals 1, if k equals 1, then we get p plus 1 choose 1 is going to be p plus 1, which is equal to 1 mod p. If k is equal to p, you get p plus 1. You again get p plus 1, which is going to be equal to 1 mod p. And then in all other cases, these two are 0. So if we have numbers strictly between 1 and p, then this entire thing here will be, like, both of them will be annihilated by the fact that there's a p in the numerator, both of these terms. So if k2 is less than equal to p, 2 is less than equal to k less than equal to p plus 1 or p minus 1, then this is equal to 0. Okay? Well, it doesn't, the k's that we have to worry about, because we're only worried about odd k, the k's that we have to worry about are p and k equals 1. Okay? P plus 1, sorry. If k equals p plus 1, what do we get? We get p plus 1 choose p plus 1, which is 1. But luckily p plus 1 is even, so we don't need to worry about k equals p plus 1. So the only two that we have to worry about are k equals 1 and k equals p. So this thing tells us that, so 2 to the p plus 1 is 4, right? 2 to the p minus 1 is equal to 1, so 2 to the p plus 1 equals 4. So we have 4 f p plus 1 is equal to 2 times, and then we care about the term where k is equal to 1. So this is going to be equal to 1, and you get 5 to the k minus 1 over 2, which is 1 minus 1 over 2, which is 0. And the other one is when k equals p, in which case you get 5 to the p minus 1 over 2. And p plus 1 choose p again is 0. Is 1 mod p. So that's what we get here. Let's make a new page. So yeah, 4, I'm just going to write this again. So 4 f p plus 1 is equal to 2 times 1 plus 5 p minus 1 over 2. Okay. If this is equal to the Legendre symbol, right? So if 5 is a square mod p, okay, then 4 f p plus 1 is equal to 2 times 1 plus 1, right? If this is equal to 1, then that's equal to 4. So f p plus 1 is equal to 1. Okay. Have I? Yeah, okay. I guess I'm doing the cases in the wrong order. If fp plus 1 is equal to 1, we already know that fp is equal to that, right? Legendre symbol, which is also equal to 1. So fp minus 1 is equal to 0. Okay? And that's what we want to show. So that's actually the harder case, sorry. We want to show that if the Legendre symbol is 1, then fp minus 1 is equal to 0. The easier case is actually when if p is equal to minus 1, then 4fp plus 1 is equal to 2 times, well, it's 1 minus 1 equals 0, so fp plus 1 is equal to 0, and that's exactly what we wanted, right? So this is equal to fp minus the Legendre symbol. And that's it. So we've proven both cases. So yeah, in either case, fp minus the Legendre symbol is going to be equal to 0 in fp, which means that it's a multiple of p, which is something that we saw way at the beginning, that f of p minus the Legendre symbol seemed to be a multiple of p for all p, and this includes 5, but I'm not even sure if actually our proof required that p is not 5, but whatever, we've already shown the case p equals 5 separately. And so that's the end of this video. That shows a little bit of a cool link between Fibonacci numbers and something from number theory, the Legendre symbol, which is a huge it's a great tool in number theory. It's the basis of the quadratic reciprocity theorem that you see in number theory courses. And yeah, there's actually a proof of this fact, Fibonacci numbers modulo prime equals the Legendre symbol, just through like algebraic number theory, which I admittedly don't know a whole lot about, but I want to learn more. And it just kind of analyzes the polynomial here. So we had some polynomial here. And, if you've got a polynomial, you can do all kinds of, nasty algebraic number theory to it. And from that, just like some Galois theory associated with it, you can find that it equals that Legendre symbol. And that's pretty cool, honestly. Yeah, I don't know, once again, I don't know too much about it, but, you know, maybe I could, if I learned more about it, maybe I could make another video proving the same thing, but through the algebraic number theory, from that viewpoint. Okay, but this is a combinatorial viewpoint, more down to earth. We also learned a thing or two about generating functions. If you've never seen that, it's a really good sort of rabbit hole to get down. They're very useful in combinatorics. Okay, so kind of a combinatorial proof of a Fibonacci identity modulo P. All right, so have a nice day.